All right. So welcome to our new home for the semester. We will be here on Tuesdays and Thursdays, M106. And we get the advantage of having this beautiful new screen for writing. So, okay. So welcome. So we are going to start talking about sort of the data structures and algorithms of database management systems. And we'll start from the basics. So talk about how data is stored on disk. And we started a little bit talking about the disk structure last time. And then we'll go into indexes and we'll start talking about sorting. And these are sort of, how do you say, basic components that we need for any kind of query processing. We need to be able to sort data for various things. For example, when you issue an order by, data gets sorted. For some of the joins, you might get data sorted. We need an index to speed up data access. And of course, the whole thing is stored in disks and in files on disks, and so this is what we'll start with. So we talked about the memory hierarchy last time. And so we had the question of why don't we store everything in main memory? And the answer was that it costs too much. And also when you turn off the computer, main memory goes away. We talked a little bit about the disk architectures. And in particular, we talked about the costs of accessing a disk page. So we had the, remember we had the, let me see, seek time, rotational delay, and the transfer time. And we talked about the differences between random accesses, where you have to pay the seek time every time, and sequential accesses when you can, when you only pay the seek time once. So just to, so the average time, seek times varies from 1 to 20 milliseconds, rotational delay from 0 to 10 milliseconds, and transfer rate is pretty quick. So if you do the math, how much would it cost you, assuming, for example, that seek time, all right, is 5 milliseconds, and that rotational delay is also 5 milliseconds on average. How much would it cost you to read 10 IOs of 4 kilobytes? Can you do the math quickly? Well, 10 IOs, so you assume that you have to pay the seek time. So they're small IOs, you don't know where they are. What would be the average cost? So one IO would cost you 10 milliseconds, right? Because you pay the seek time and you pay the rotation delay. So the 10 times 10 milliseconds, so which is, well, 0.1 seconds, right? I like the pen, it's writing slightly to the right. It's a little bit confusing. All right, same amount of data, but one IO of 40 kilobytes. How much is that going to cost you? So you pay the seek time, which is 5 milliseconds, and then you actually have to pay the rotational delay, which is 5 milliseconds, and then you get into some transfer time, which it's hard to tell what it is, but it will be less than one rotation, so it could be maybe on the order of 5 milliseconds. So this is 0.015. If you actually issued 10 IOs on the same track, then you'd sort of have to pay the rotational delay maybe a few times. In practice, random I/O is roughly 100x sequential I/O. So when you do the calculations, they come out to roughly 10 times, but in practice, you find that it's really 100 times more efficient to do sequential I/Os on random I/Os. So that was really the motivation for why I/O really matters. And then we started talking a little bit about how do you reduce the I/O cost. And the first solution, which is software solution, is basically thinking about where you put data on disk. And defragmentation is sort of an application of that principle. Just put things together so that you can avoid the seek times and the rotational delays. And that's a software solution, and it's based on this next block concept. So assuming that you are, so we have the disk here, and we have a track, and we're reading a particular sector. So assuming that you're reading this particular sector, what's going to be the next one? Well, it's going to be this one, right? Assuming that the disk is spinning in this way. And then after that, you get to this one and so on. Once you've read all the sectors on the same track, on the same platter, what's the next sector that you'll find? Basically below, right? On the next platter, and so on. Once you've done that, what's the next sector? Basically the one side by side, right? You just move the disk heads as little as possible. And it turns out that the mechanism for moving disk heads a little bit is different from the one of seeking really far. So there's a way to just move it slightly, which is faster. Don't you usually start at the edge of the platter? It would probably depend on whether that matters. Would depend on the implementation of the disk. If the disk has the same density per square inch everywhere, then you would get basically more data on the edge. If the disk has sort of fixed, puts the same amount of data on every track, then it doesn't really matter. Yeah, so the rotation is constant, which means that actually the speed of the metal here is faster, which means that, again, some disks will pack the same into sector, basically into the angle, regardless of where on the platter it is. And so in that case, it's just less dense on the edge and more dense in the middle. Other disks will basically have the same density everywhere, which means that you will have more data and the transfer time is shorter on the edge. And so that's going to depend on your disk more than anything. Now, if you do have this, if you do work with the same density, then yes, actually it will be better to have more data, push the data to the edge of the disk. You're right. But basically, this next concept is sort of independent of where you are. Just if you're here, then the next over is there. But you're right. If in many disks, it would be preferable to push the data to the edge of the disk. Very good. And so the point of this is that for a database management system, it typically pays off to pay a little bit in the writing of the database to save in the reading. So the database system will typically try to order things together so that the reading will be faster. So that was one solution, and as it turns out that in particular when we have good ordering on disk, then we can do something called prefetching. And this is what operating systems do actually quite a bit, and database systems as well, is that if you read a particular page, they will just get in more data than you asked for, on the assumption that the next thing you'll use is that. And for example, if you're scanning a large file, we can go back to this example. So you read the red thing, what actually gets read in is this. And if you're scanning, then this will be a big payoff because you won't have to pay another I/O for a while. If you're reading a large file and you detect a pattern where you're reading through a large file, then the database system will just start going ahead of you and will try to stay ahead of you all the time, so that when you're reading, you'll never have to wait. And this is called prefetching. Can be a big save in many cases. And then we have hardware solutions, and these typically come in the form of RAID disks, and now recently you have sort of layered disk solutions where you might even have main memory at the top, you have solid state disks, and you have hard disks at the bottom. The abstraction of RAID, so who's familiar with RAID? A little bit, yeah. So there's basically two main techniques. One is called striping, which means that the data is sort of shifted on different disks so that many read heads can be working at the same time. And the other one is redundancy, having more than one disk storing the same data, so that you can again call on more than one disk to do this. And there's something called RAID levels. Level 0 is no redundancy. Level 1 is mirrored. It basically means that for each disk you have another disk that just contains a mirror. If you're writing data to the disk, you need to write to both of them. If you're reading data from the disk, you can read from either one of them. And then if one of them crashes, you still have a copy, right? So that's the advantage of RAID 1. It's just mirroring it. You sort of, on disk failure, you have a backup copy immediately. And then there's something called level 10, which is, so level 0 is no redundancy, but it basically stripes the data so that part of the data is on one disk, the next page on another one, the third page on the third one, and so on. And then level 10 is striping and mirroring. With what this means is that where did my pen go here? You have many disks, and for one file, the data pages are on all of these disks, and then you have mirroring of every one of the disks, and that one also has copies of the data files. My drawing is worse than usual because of the shift. So this is also called, I think the Oracle has the terminology called SAME, stripe and mirror everything. And this is, if you want to be sort of safe in your data storage solutions, then you just do this. It has redundancy, it has performance. This RAID 5 is still used in particular when you have high read access and less write access, I think. So this RAID 5 is basically, there's parity blocks, so you don't mirror everything. You have, if you need 4 disks, let's say, then you have 5 disks. And so one is a parity block. So the data is here, and then you store parity, basically. And then you rotate the parity block. One of the advantages of SAME is that for every disk, you always have 2 read heads. And so you get better performance with this. Redundancy comes basically in the form of mirroring rather than putting parity blocks to discover errors. But it's more expensive because you need more disks. These days, how much does a disk cost? you know, in terms of the budget of a large company, zero. It really doesn't matter. So I think RAID 5 is still being used for very large solutions, sort of at the bottom where you need massive data amounts, but this is what you get in most companies. So you're clear on the level 10? This is really the key to take home, and this is a hardware solution to reduce cost, because you can basically, if you're reading a large file, you might potentially have all the read heads working on that scan at the same time, because the file is distributed to all the disks, and you have 2 copies of each page. That means you can basically, in this case, have 8 read heads reading your file, which is 8 times faster than having a single disk. Will it work that way? It's got. In practice, will it work that way? It could. It will depend on the implementation. It will depend on what else the disk stack is doing. But in a solution, if you have a good, expensive disk solution, then they will typically be working all together at the same time. The question is just what are they serving? It's a great benefit to reading. Sometimes it's a little bit slower to write because you always have to write 2 copies. And if one of the disks, for example, is particularly busy, you kind of have to wait for that disk to finish before you write. And so a good solution will typically have buffers, for example, where they just sort of might have a solid state disk to keep track of to buffer the write so that you don't have to wait. Yeah. Well, if you have 2 disks, then typically you actually would have level 1, which is just a mirror. Yeah. So you don't. Then that means you're not striping the data to many disks, but you do have the mirror. And yes, yeah, and in fact, I mean, the mirroring basically happens so that the writes are issued to both, and they both have to complete. So it's not really that I think one is superior to the other or sort of first. Yes, yeah, and that is the disadvantage of the stripe and mirror everything solution, is that you need twice as many disks. And what you do get is the redundancy, so that if there are failures, then things keep on running. They might be a little bit slower because that means you only have 1 copy of some of this. A good stack, if you find a disk failure, then what they do is you just take the disk out, you plug another one in, and it starts copying to it, and then it slowly gets into operation, so that it's seamless. It's the things might run a little bit more slowly, but you don't have to worry about this. So that was the hardware solution of improving the cost. Now the solid state disk, we were running very fast at the end of last class when we started talking about this, and it changes slightly the trade-offs between reads and writes with solid state disks. So basically, in hard disks, it doesn't matter whether you're reading or writing, the costs are the same. Or solid state disks, reads are always fast, regardless of whether you're reading sequentially or randomly. Sequential reading is slightly faster because there is less. Somehow the software is faster, but the difference is small. Sequential writes on a flash chip is usually fairly cheap because there's nothing that needs to move. You're just writing to silicon. Whereas a random write, because of the way solid state disks are built, you cannot just write. You need to you basically can only change bits from 1 to 0, and so you need to sort of erase large segments of the disk so that you can start writing. So the details of this are not very important, but basically random writes are pretty expensive. So rather than both random reads and writes being expensive, only random writes are expensive. Now, if you get sort of cheap low-end solid-state disks, then you will see this behavior. You will see random writes being very slow. If you get really good solid-state disks, that will cost you, maybe a few million ISK, then they just hide this. And what they do actually is that because the reads are fast, you don't have to worry about sequentializing reads. So what they do is they just write sequentially. So regardless of where you think you're writing on disk, they will just write this like a big log file. And then when it comes to time to read the file, they will go all over the disk to get it. And this is, excuse me, is that implemented in most disks today? The question is how good they are at hiding this. And are you talking about hard disks also, or just solid state disks? Yeah. So I don't know, maybe. I wouldn't think so. I think it really depends on what you pay. But you also, because even now, you also find file systems that are trying to do this behavior on top of solid state disks. So, but I haven't tried them and I haven't looked at them. They don't tell you too much. But I still think that if you buy cheap disks, the random writes will be slower. But I might be wrong. The only way is to measure. That's the easy way to find this out. But these things are becoming practical. There are solid-state disks of terabytes now that are, not horribly expensive. And so if you really need performance, you can really get performance. All right, so that was just to do a better job of what we talked about last time, because we were really getting into a hurry. So then continuing sort of with the bottom layer of the database management system software, what you find at the bottom is the disk space manager. And what does that do? Well, it's basically the system when it needs a page, it asks for a page, and if you need to read or write a page, that's what it goes through. And the sort of the order of the day for the disk manager is to try to make things sequential, right? Try to organize things on disk such that you will get the sequential writes. And that's really the key role of the disk space manager. Higher levels don't need to know how it's done, don't care as long as it works. And so I think the typical things of a disk space manager is to work with some kind of extents, so that when you ask for the first page of a file, you don't get one page, you get lots of pages. It's an extent of pages. And then it's working within this extent. And if you need another, when you fill that up, you get another extent somewhere else. And the extents are large enough that when you read the whole extent, you get most of the benefits of sequential IOs. Even if the next extent you have to pay one disk seek and rotational delay, the extent is large enough that this cost is not high. So 64 pages, for example, or something like this. And I think the OS now does something similar to this. I think Linux, for example, if you read something, it typically reads in 32 pages. Just since we're going to this, we might as well. Yeah. So the question is, are we paying for this many times because we're buffering? So I mean, you might say that the disk buffer is somehow managing this. I mean, it's retrieving this. Then you have the operating system, then you have the database. Many database systems actually forego the operating system buffers. They just say, we'll do it ourselves. I mean, Oracle works, or at least used to work best with raw partitions, where it just got access straight to the disk. Microsoft SQL Server, I actually believe that uses Windows buffer management service, and probably there is some special things in the Windows buffer manager that nobody except Microsoft knows about that really improve the SQL Server. So at least that's one thing. And then I think the disk buffers are typically used for writing actually. So when you have to avoid waiting for a write to make it to the hard drive somewhere. So I think that's the typical use of this, and rather than reading actually, because I think the reads just go straight through normally, and so this is just to balance out the cost of writing. Yeah. So again, I think the disk buffers are not used to store data. I think they're used to even out the cost of things, and as soon as things make it to disk, it's gone. Good question though. So that was a disk manager. Now, if you think about the impact of disks, I mean, the key is that the computer works with data in memory, but the storage is on disks. And then you can ask, where does this impact us? Well, the first thing we need to do is the buffer manager that you talked about, and we need to manage this. We need to worry about what's in memory, including prefetching and all this stuff. And the second is we need to organize the data into disk pages. That is, we have these fixed size blocks of space, even when the data is in memory, that we need to pack our data into. And this sort of causes some troubles. For example, if the records are variable length, we have a varchar or something that might range from 0 bytes to 150. It's hard to pack. So are you familiar with bin packing algorithm? Okay. It's basically, how to optimally pack data into fixed size bins. It's NP complete. So you know that, you heard of that concept, which means that it's really hard to do, optimally. And so we don't try to do it optimally, we try to do it reasonably. But that's really, what this chapter is about the impact of data being on disk and computer working with it in memory. And that's really the key trade-off in this. So the buffer manager is essentially a part of the memory that is, or most of the memory that's organized into what's called frames. And the frame is roughly some small overhead, some booking stuff, and then it's just the disk page. That's a frame. It's an array. I mean, you think of the buffer manager as having an array of slots that could fit a page. And when we have a page in there, we need to know which page it is. We need to know whether it's been modified. We need to know whether it's actually being used currently by somebody. And so this is the kind of bookkeeping information we have. So imagine that you are a database system and you want to access some kind of record. And then, so what you do, I mean, you identify the page that the record is in and you ask for that page. Now the page could be in memory, in which case you just get a pointer to it and you can access it. If it's not in memory, what you need to do is to bring it into memory. And typically the buffer is full so that some other page has to go. So you're familiar with virtual memory, right? Paging, if you fill the memory of the computer, you have to put stuff on disk. It's basically the same thing. So the buffer manager decides this page, it can go. maybe it was only accessed a long time ago. I can let it go. Or for some other reason, the buffer manager says this is a candidate. Now, if that page is dirty, if it's been modified, then the buffer manager has to write it to disk. And then once you have freed up the frame, you read the page into the frame and you give back the pointer. Are you with me? All right. So again, if the buffer manager might decide to prefetch, so just drop a few pages and prefetch, but this is not a concern of the database system. It's just gets the pointer to the page and it continues working. Then once we do this, the page is pinned. And what's a pin? It's basically a counter. So again, remember we have the frame, we have some information. There's something called the pin count. And you just said, okay, shit. You just say, this is now 1. If some other page comes, ask for it. This is now 2. Third page comes, request the data, 3. Then you've done using the data. You say, I can let it go. All right, we go back to 2. See what I mean? Just how many people are using or how many transactions or queries are using the page. That's your pin count. Now, which pages can be replaced by the buffer manager? How do you know whether you can replace a page by the buffer manager? 0. Pin count of 0. That's it. Nobody's using it. So those are the candidates. What happens if you have no page with a pin count of 0? You have to wait. Yeah, that's it. Just wait. You're using all your resources. You cannot do anything. You just have to wait. Okay, so that was it. And then again, you have something called the dirty bit, and that's either 1 or 0. So when you read in the page, it's 0 because it has been modified. If some transaction modifies it, you get the value 1. Yes, then you have to write it. So basically, if frame is dirty, you have to write it to disk. If the page is dirty, you have to write it to disk before you can let it go. So the impact of this is that if your replacement is dirty, it will take a longer time to get back your page. You have to take a page, you have to write it to disk, and then you have to read your page into memory. So that's kind of bad, right? So how can we get around this? How could we avoid paying 2 IOs instead of 1? One option is to write everything as soon as you can. And actually, typically, a database management system has a background thread that is sort of going around and looking at if a page has been in the buffers for a while, modified, then it will write it to disk. So, there's typically a thread going on trying to do this. It typically doesn't do this immediately because sometimes you have many writes happening to the same disk and you want to avoid writing the page many times. So it typically doesn't do this immediately. So it's mostly if a page has been written a while back. So they might actually keep track of when, or see what I mean? Or if it's a page that hasn't been used for a while. I think that's relative to your workload. So basically we'll get to how you do this, but there's something called the least recently used queue. And so, the things that are most recent are here, the things that are least recent at the other end. And so things that are moving to the back of the queue, those are ones that haven't been used for a while. So that's one way. The other way that could potentially be done to avoid paying the 2 IOs. Any ideas? So what happens if your replacement is dirty? You might basically try to pick pages that are not dirty. So you might avoid, if it's possible, you might avoid picking pages for replacement that are dirty. I think the other one is more common, that you just have the thread that's trying to keep the buffer manager or the buffers reasonably clean. So, and in particular, there might be some kind of threshold. If the level of dirty buffers goes up beyond, let's say, 20%, then you start the thread to clean it up a little bit, just to avoid this kind of effect. So that's the buffer manager. So it's important to unpin. It's important to mark set a dirty bit, and then we'll get to the fact that when you're doing concurrency control and recovery, there might be some additional IOs involved, logging and things like this. So, the frame that you choose, this is typically based on something called LRU, least recently used replacement policy. So that the page that you want to get out is the one that has been in the buffers for the longest without being used. And the way to do this is that you have a doubly linked list of all the pages in memory. And when you use something, you pull that to the front of the list. Or if you read in a new page, you put that in the front of the list. And that means that that's the most recently used. And then they get older and older as you go further in the back. And when you're replacing, you just go to the tail of the list and you say, that's my candidate. Do you have to lock it so it doesn't change when you're reading? Basically, yeah, but you're right. I mean, do you have to lock the page to avoid reading? You do. Now, what the assumption that at least the buffer manager of a database system can assume is that there's locking going on in the database server, so that that sort of takes care of this for you. What is common, however, is that you have these semaphores that you'll talk about in operating systems, maybe, or even in computer architecture, so that which are just sort of very short locks, so that while you do the actual modification, nobody is reading the data or writing the data that you're modifying. Good question. So I had some examples of buffer manager here. So just to visualize this a little bit. So at the start, you see the memory buffers that we have at the right, which are empty. You have the file, which has more pages than you can fit in memory. And then you have these least recently used and most recently used pointers that are pointing to the one of the end of the queue. So, so you start by reading page 1, and the request goes from memory to disk. The page goes into memory, and now actually both of them point to 1. And whoever requested page 1 gets a pointer to the frame. You ask for page 2. This goes into another slot in memory, and now I can see that this is the head of the list. This is the most recently used, and then there's a doubly linked list here indicated by the arrow with arrow on both ends. You ask for page 6. Memory fills up. It's loaded into memory, and the list becomes longer. You ask for page 10, and now your buffers are complete, right? So you get this nice organized Hilary list. You read page 5, and so what's the least recently used page is 1. This is the page that has been the longest in memory without being used. So that's your replacement candidate. You drop that because it's not dirty. You can just let it go. And then you read page 5 into that slot, and you modify your linked list. Read page 2, same thing happens. No, actually, page 2 is already in memory. So the only thing that happens now is that you update your linked list information. You take 2, which was actually the next candidate for replacement. It's the least recently used page, and you move that to the front. So it's now the most recently used page. You clear? All right. So you write page 6, and writing means that it's recently been used, and so that's now the most recently used page. Nothing else happens. You read page 3, so you have to replace page 10. You read page 4, again, you're just reading, dropping pages, updating. Read page 5, and you observe this. Here we have page 5, we read 3, we drop page 5, then we read page 5. So we just dropped it. We just got unlucky. It would be nice to have slightly bigger buffer so that it was still in memory, but sometimes we get unlucky. We just drop some things and we have to find them. Now, when we read something in, then you can see that the least recently used thing is 6, which is modified. So when we read another page, we have to write 6, then we have to read 7 into the buffers, and so on. Clear? Okay. Now, we observed in this that sometimes we get unlucky and we just dropped a page. Now, there's something called sequential flooding, which is really sort of a nasty example where we are repeatedly reading some page that is a file that is larger than the memory. And if you try to visualize this, you read the front of the page of the file, you read the front of the file until your memory fills. And then you continue reading, and what you have to drop? You have to drop the front part of the page of the file. Let me see if we can get it. And then when you get to the end of the file, what have you dropped? You've dropped all the front parts. So when you go and read it again, the end of the file is in memory, but you have to read the front of the file. By the time you get to the end of the file, you've dropped that. See what I mean? So I actually had another example of this. Sorry. Yeah, here. Just to visualize this. So it's just a case where the file is only one page larger than the memory. So it's particularly painful. So you read 4. When it's time to read 5, you drop 1. See what I mean? Next page, 1. Shit. You drop 2. Bad idea, right? And in fact, you kind of know that you're going to read 2, and so in this case, LRU is actually the worst thing you can do. Can you think of a better policy in this case? Here, what should you drop? Which page should you drop? You should drop 4. And what is 4? Yeah, it's the most recently used. That's the name. It's the MRU. So that would actually be a better policy if you're doing repeated sequential scans that might happen in joins, for example, is to do the MRU. And that basically means you sort of keep the front of the file. And then the rest you just ignore. And in fact, some systems will do this. If they detect or are aware that there's going to be a sort of a looping behavior, they will use MRU for that particular thing. Or in other cases, what they'll simply do is when you're scanning a file, is that they don't allow you to empty out the buffers. So in this case, for example, if you had decided that this scan would only get this buffer, and these are just reserved for something else, what would happen? You'd basically pay the same cost anyway for the scan, but everybody else would be still pretty happy, because what happens here is that the whole file gets flooded and emptied, and you clean out all your buffers. Everything else that anybody else is doing is gone, and that's really the bad behavior. So there are 2 alternatives to deal with this. Do you get like an abstract virtual memory for particular tasks? So a database management system might allocate, different parts of memory for different tasks. It sort of depends. And some systems, I think Oracle, for example, it sort of partitions, says for these kinds of tasks, you will only get this much buffers. For these kinds of tasks, you will only get this much buffers. So they do things to avoid, interactions that are really bad. And I think, for example, SQL Server, when it detects the scan, it will just allocate, uh, a small chunk of memory for you, enough to do the prefetching, so that you get the benefits of that, but not enough to fill everybody else. Is this a problem with where you have gigabytes of RAM for the database? Well, if you have terabytes of data. Right. So if you have, typically if you have short transactions, then it's not a problem because they access small parts of the database, and so, it's just a matter of putting out the data of some transaction that was in the past. Really, the problem comes with these large scans or large operations that are doing this. Is it a problem in modern systems, you asked? No, because they do something, they avoid it. See what I mean? And so the reason why we covered this is that so that you can read about the techniques that they're applying and understand what is happening. But no, generally, for example, like I said, this is such a well-known case that it's avoided. And in fact, so before we take the break, this is maybe the last slide. Why would we do buffer management in the database system rather than just delegating this to the operating system? And the reason is exactly that the database system knows. It has a query optimizer that's telling it, or query processor that's telling it, this is a sequential scan, or this is not this is an index access, or so on. And so the database manager can optimize buffer management because of the knowledge that it has of what's going on. And this is why we don't really have a problem in the modern system, but it's really good to be able to decipher when they're telling you that they apply, particular buffer management to these kinds of queries. It's really good to know what's going on. Okay, let's take a break now, 5 minutes, and then continue. Yeah. All right, so that was the buffer manager. To me, buffer management is really the sort of the big impact of having data on disks and not in memory, or working with them in memory. It does have an impact on record formats, but this is kind of just data structure issues, and I mean the impact is that sometimes you have space that you lose, and you can't use. So the alternatives for record formats depend on whether you have fixed length fields or not. If you just have fixed length fields, then it's kind of easy to just have fixed length records. That's a short way to do this. And if you want to find a particular field, then you can just jump to that field and read it. And you know how long it is, so you can just read the bytes that correspond to the field. Now, the information about the field types is stored in something called system catalogs. If you are in SQL Server, it's something called sys objects that you can select from just to see what are the tables. There's something called sys indexes and so on. There are many tables that have these information. But if you have a fixed length, it's easy. Now, typically you do have variable length when you have archive records and so on. And then you can have two formats. One is to say, the fields are delimited by some special symbol. The other one is to say, well, you have pointers to the start of the field and then one extra pointer to the end of the last field. So this is pointer to the start of field 1, this is the start of field 2, end of field 1, and so on. So these are typically just numbers that indicate how many bytes there are. So if you want to access a particular field, you can just go to the slot here, go to the start, and then read until the next pointer. If you have a null, two pointers will be the same. That's easy. There's no data. There's a little bit of an overhead here, but there's also an overhead here. So the overhead is kind of similar. If you want to access a particular field in this format, then you basically have to scan until you found enough special symbols, and then you start reading and read until you find the next one. So this one, I think, this is basically what systems use, and some systems will put all the fixed length fields first and then all the variable length fields. Others will just deal with fixed length fields as they do with variable length. Yeah, question. Yeah. Could they not split the fields so that they have all the fixed fields basically somewhere and then maybe all the variable fields somewhere else? They could, and in fact, for something called blob, they do. So if they have it's binary large objects. So if you have a picture into the record, then that's typically stored somewhere else. Now, if you have varchar fields, they will be stored with the record, and the reason is just to avoid two IOs. So the blobs can be so large that you probably have to do some IOs to get it anyway. And it's very common that things like pictures are not accessed generally when you're scanning the file or the table, but you will use them to get specific blobs. So it makes sense to put them somewhere else. But I don't know of any system that would separate a particular record into two parts, except there's actually something called column store, which really just stores the columns together and not the records. So we'll get to that at the end of the file. But this is so you will see things like there are typically limits to the size of varchar entries. Each record can only be 8K bytes roughly, because it has to be stored within a single page. So, but in theory, yes, they could do this. Now, that was the record format, and then the page format is similar issues. If you have only fixed length files, then you have two fixed length records. You have two alternatives. You can either basically keep all your records here, and if you delete one, see, if you delete one, oh, come on. What is this doing? Yeah. Sorry. Oh. Okay. What can I do? If you delete one, what you have to do then is to move the rest up one slot. Or you can keep an array of slots and say, you know, a one here means that it's actually used. So yeah, this one is in use, so that gives you, this is really this is this one is free, and so you get a 0. Now, alternatively, you have variable length records, and this in fact works for everything, is basically you can put the records anywhere in the page, and then at the bottom or at the end of the page, you have an array of pointers that show you where the record is. And this can work for anything, and if you decide to move a record, then you actually just have to change the corresponding pointer here. And so I think this is the format that all the systems are using. If you add one more record and you have a space for that, you can just add one more slot to the array, and you add one to the number of records here. So it's a very flexible format. But again, this is just, it's interesting to know. Key question actually that you had is whether you can separate it, and it's good to know that these binary large objects, they are somewhere else. If you need to retrieve them, then you will be paying extra IOs. So if you know that, for example, there's a binary large object in a particular table, then doing something like select star would not be a good idea, right? For every record, you'd have to pay 2 IOs. You would be paying a lot of IOs to do this. So then enumerating the fields that you actually want is good. And then once you have identified that you need a particular page, then you select the blob for that particular record. All right. So this file select okay. Then you have these pages, and now you need to store these into files, and the question is, how do you organize that? And basically, you keep a track of all the pages in a file, and you can what's important actually is to know where you have free space, because when you add a record, you need to go somewhere and put that. And so there are two ways to do this. One is to say, here are all the full pages, here are the pages with free space. Within each page, you'll find out how much space you have. Or you can have a directory, which is kind of like a file system. The key is there's, in the particular file that's storing a relation or a table, you need to know which pages are full and which pages have space. That's, I go through this in more detail. It's basically, again, the impact are the buffer manager. I want you to understand the buffer manager. The records are nice to know, not very important. Buffer management, extremely important. All right, so any questions about this? Oh, okay. Then we can start talking about indexes. So, yeah. Yes, you can both say indexes and indices. Indices is actually the correct one. Indexes is the lazy American one. So that's a good question. I'll actually get to that. This is part of the jargon page. Yeah, it's a good question. So yeah, indices is the correct one. And so you'll find this in many cases. But Americans tend to be lazy about this. All right. So why do we have indexes or indices? So I think I tend to write indices most of the time, but I say indexes. Anyway, yeah, writing is more formal than speaking. Well, the reason we have indices or indexes is that, again, we need to bring things into memory, and I/O is costly. So if we can do something to reduce the number of I/Os, it's really worth spending some effort to do this. Now, the numbers here, tuple and buffers, probably more expensive, and tuple and disk, the difference is getting larger as CPU and memory become faster because the disks are slow. So indexing is basically some kind of data structure that allows you to identify your set of records, your pages or whatever, quickly. And typically an index has some kind of search key, could be a hash key or something that you organize a tree with, that you use basically to make your way through the index somehow, find a pointer to disk where you can retrieve your record. That's how you use an index. Now, the typical index that you've all used is a telephone book. Actually, maybe you haven't. Maybe you only use the electronic version. But you've seen the book, right? It's good when you have a name and you need to find a number. Is it any good when you have a number and you need to find a name? Not very good. You can use it, right? You can indeed start reading the 3 columns, first page, until you find the number, and then you can look up the name. But it's not a helpful index. Now, there are 2 techniques used in databases. One is hashing, where you have this fixed transformation that just basically you have a calculation that gives you the address. And the other one is the tree search, which, there's a structure, data structure, that you go through to find the address. I was asked at the break, is there a way to get database systems to allow us to create hash indexes? And the answer is typically no. I mean, the databases use, the only thing that users can use is tree indexes. But we'll find out when we start talking about join processing, for example, that the system itself will create hash indexes. So I want to talk basically about the tree search and about B+ trees, because you've seen many trees, but you actually haven't seen B+ trees. And this is the most common index. It's very good for equality range queries. It's a dynamic structure, meaning that it's basically maintains a balanced tree. Have you talked about balanced trees? Balancing trees, like, you can balance binary trees, for example, by shifting things around and so on. This is a similar thing. It's actually not shifting things around, it's just growing up and down uniformly. But the key thing is that it maintains a balanced tree. And this is good because that means the query optimizer can know how many IOs there are from the top to the bottom. So it's sort of a controlled behavior. Now, the reason for the particular structure, again, is because data is on disk and you have to work with it in memory. And that means the nodes, for example, are quite large. The nodes are typically a single page. So 8K, 4K, depending on your operating system. Well, this is in contrast to, for example, 2, 3 trees or something like that, which has a very small node, or a binary tree has a very small node. It's a main memory structure. So that's one thing. And the other thing, basically, the fact that you're going to dismotivate the need for the balancing, so that you don't want the bad behaviors that can come when you have unbalanced trees, where in some cases you might have to read many IOs to get to the bottom. Okay, so I think that was motivation, jargon. We'll talk about the index versus indices and so on, then go through some of the B+ trees. So that's the jargon. So index versus indices, same thing. So you remember primary key and candidate key from your first database course. candidate key is basically anything that you uniquely identifies a relation or a record in a relation. Primary key is one particular key that was chosen to be number one. You're number one, you're the primary key. The other ones are, secondary keys. Remember this one? Okay? And then in an index, we might have a search key, and this is what we use to look up the records in the index. It doesn't have to be a candidate key. For example, in the telephone book, your search key is name. It's not unique. It's not unique, but it's it's what you need to find the data in the index. So that's a search key. Clustered index versus unclustered. So you were measuring something yesterday. Did you use two different indexes to see some different performances? So clustered index basically means that the order in the index is the same as the order on disk, so that when you're scanning the index, you get sequential I/O. Unclustered means that the first thing might point here, the second thing might point here, the third thing here, and so on. So there's no correspondence between the order of the index and the order in the file or in the table. What does it mean in terms of performance? This is sequential, that's random. So, and that's it. Primary index versus secondary index. Any ideas? Yeah. So basically same as primary key and other keys. So that's when people refer to primary index, they're typically talking about the index for the primary key. In many systems, that's by default a clustered index. SQL Server, it's by default a clustered index. It's not necessarily a clustered index. You can choose. You have one primary index and you have many secondary index because the primary index is the primary key index. Yeah. Unique index versus non-unique. Basically, any index that's for a primary key where the search key is a primary key or a candidate key, that's a unique index. So an index on Kenitala or some IDs, that's typically a unique index. Non-unique index on name. Any value that's non-unique. Dense index versus sparse index. If your relation is ordered on disk, then the index can in fact point just to the first pages or the start of the pages. See what I mean? Because the data that's here is going to be between these two values. And that's a sparse index. Dense index, you have to point to every record. This one doesn't matter too much. Then we have something called a spanning index or a covering index. This is for query optimization. If the index has all the columns that you need for your query, then you don't have to go through the actual relation. So we talked about this in the course. So if you are, let's say that you say select ID from relation and that's it, and you have an index on ID, then you can just read the index and you don't have to read the actual relation. In that case, that's a spanning index or a covering index, so you don't have to go through. So this just, you'll see these words at some point, so sort of a quick review of what they mean. We will find that this one is really important. For performance, that one makes a huge difference. Clustering versus non-clustering. Because if you're reading a fair chunk of the relation, then clustering means sorting, and that is very important for performance. It means sequential IOs. Yes, there can only be one clustered index. Absolutely. Because you can only order things in one way at the same time. I don't remember. I was asked what Okay. 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 Yeah. Okay. It could be. So I'm asked whether I meant spanning index in the last part of the homework, and then I have to admit that I don't remember, but we can check this offline. But basically, if you, in particular, if you have very large records in your relation, so there might be some IDs that are small, and then you have just these long strings, logging or something, then using a spanning index that is looking at just a few things might be a huge saving. It might be much more efficient. So that's one thing that you can look for is if you're improving performance is to use these covering indexes or spanning indexes. All right. So you'll also see some query jargon, point query, that gives you just one record. I want to get employees where ID is equal to 25. That's a point query. I want to get all the employees where the department is 15. That's a multi-point query. There's still equality, but you will get several things. Range query, I want to get all the employees with salary from 3,000 to 5,000. Extremal query, I want to get the employee with the highest salary. Prefix match query, this relates to indexes. It's basically a query with equality signs on the first column of an index, or first two columns of an index. Grouping query, aggregation, right? Group by. Ordering query, order by. Join query, join. So just so you know what to mean. So these ones you've all seen. The prefix match, again, if you have an index on, let's say, on columns A and B and C, and you do select A from relation, then this is a prefix query. It will be easy to use this index to answer that. Yeah. Okay. So you're saying if you had something like select select, let's say star from R where, and you say name like B%, something like this. I don't think that's what they mean, but actually that's for this you could use an index to answer if you have an index on name. If you have the query like this, then you can't use an index to answer it. So maybe, but both are actually important and make a separation. So this one, again, you can use an index. This one, you can use an index. So they have that in common. So regardless, prefixes are good, basically. Yeah. Okay. Yeah. So the like is basically a regular expression of sort. It's a limited regular expression. So B% means anything that starts with a B. I don't care what the rest is. Whereas equality, that's basically, I mean, this would match the string B% and only that string. So you can make wildcards in equality. Yeah, it's an equality. So you use like for that. So that's the difference. So this is what a B+3 would look like. So these nodes, again, this is a disk page. And this is also this page. So I draw these, in this example, this page are fairly small. I mean, these are, if this is a byte, this is 4 bytes, and the pointer is 4 bytes, how many records like this could you fit on a page? If you have 4K, you could fit roughly 500, right? So when I'm teaching this, I cannot draw. I can't draw very large pages. It's hard to fit them onto the screen. And what this means basically is that how you use this is that these represent search keys, and they say if I want to find some value, I want to find employee with ID 25 or employee with ID, let's say ID 5, then I would compare here and say 5 is smaller than 17. That means I need to traverse this pointer. Then I come here, say 5 is actually the same as 5. It's not smaller, so I need to go to the next one. 5 is smaller than 13, so I traverse this pointer and then I scan. And so everything that's to the left of a value here is smaller. Everything that is the same or bigger, that's going to be to the right. This is the rule, basically, of constructing the B+3. Now, you'll see this star, and that basically indicates typically a pointer. So you have the value 22, and then you have a pointer to the record with value 22. So to employee with ID 22. And this is denoted by a star. Remember, we talked about the 3 alternatives, how you can store data. You might have the data itself, in which case this actually would be the record of ID 22, or you can store the values. So, and for each pointer with value 22, you might store one record, or you can say keep 22 and then all the pointers. So these were the alternatives. And the star, just asterisk, just means that. So actually, I just want to go and show you just some examples, and then we'll talk about some of the details. So this is a sample leaf. It has search key, which in this case could be something like ID, and then a list of all the records that have this ID. And you can see that this tree it has a doubly linked list. You see the pointers between the leaves. Why would we have a doubly linked list of leaves? Any idea? So we can scan basically sequentially through, so that if we need to look at a large range, we can just go through the pointers and not go back up into the tree and have to go down. So this is a node. It actually also contains search key and pointers, but the pointers are to the next level. And we can say all values that are less than the node key, they're on the left. All values that are equal to or larger, they're on the right. It has no pointers to records. It's just data value. So the record with value 17, it's not here. It will be here. And now you can see actually there is no record with value 17. Why? How could that be? Yeah. Yeah. Okay. Why do you need a doubly linked list and not just a linked list? Anybody want to answer? Yeah. Yeah, it depends on the query. So order by increasing or decreasing. So yeah. So right. So you might say everything less than 19, you find 19 and you go left. Anything that's greater than 19, you find 19, you go right. So that's one way. Also order by. If you say I want to order this in decreasing order, then you might start here and then go here. So that's the reason why. Yeah. So and you know, in an 8K page, 2 4-byte pointers would not be that much overhead. So well, that's a good question. Thank you. And okay, so 17 is here, but it's not in the record. How could that be? Yeah, it was deleted. So at some point it was inserted, it's made its way up there, and then it was deleted and it's no longer there. And so, and that's the point actually. This is one reason why there's no data in the nodes, because the nodes could contain old stuff. What the nodes do is point you to the leaf. And so there is a structure called B tree, actually, where the data is in the leaves. But this is a B plus tree where you put everything at the bottom. And this also means that when you're reading data from a B plus tree, you always have to pay the IOs to go here, unless they're in buffers. So it's always a fixed cost of going to the leaf. It's the same regardless of where in the tree you are. It's also a fixed cost of going to the leaf. So searching, begin at the root, compare. So if you want to find 5, you compare that to 13. 5 is less, so you go down here and then you start scanning. It's not 2, it's not 3, it's 5. Bingo, we're done. Right? Now, if you have a unique index, you're done. If you don't have a unique index, you might have to continue. You want to find 15, you compare 15 to 13, it's larger. Compared to 17, it's smaller. So you go down here. Start at the beginning, you compare to 14. Okay, not 14, you compare to 16. 16 is larger, so you're done. That's it. It's not in the tree. Want to find all the records greater than or equal to 24, compare to 13, compare to 17, compare to 24. And again, because on the left is smaller, on the right is larger than or equal, then you have to go one further and you traverse this pointer and then you just scan, traversing the linked list to the end. Clear enough? All right. So now the intranode searching, I mean, I've been using scans, but if your tree has hundreds of values, then it might be better to use a binary search. Some actually have a little binary tree or little B plus tree inside the node. So in-memory B plus tree inside the node, but simpler. Do the nodes always have 4 slots? No. Well, the nodes will always have a uniform number of slots. But okay. So what I can pretty much guarantee you is that they will never have 4 slots, because you would have, I mean, that would mean a search key of typically 2000 bytes or something. So what they'll have is, hundreds of slots. Now, I said it's always uniform. This is actually not true. I mean, if your search key is a varchar, then you will have a variable size slots. See what I mean? So it's actually not true. What they basically try to do is to put as many as you can into a page, but what you can know is that this is basically your 8K or 4K, depending on your configuration, or even 16K. This is the database page. So then you just push as many into this as you can. There's some overhead in the form of these linked lists and so on, but you just put as many as you can, because the more you can put there, then the lower the tree will be. The wider the tree is, the lower it will be. So, good question. So, but never 4. This is just a drawing. Yeah. Okay, so which slides did I skip? Let's see if there was anything good in them. Right. So, again, I mentioned this, B trees contain record points in the index node to leaf. B plus trees only in the leaves. Means that you have to go to the bottom to find something. It means you have higher fan out, because there's no data in the nodes. So you get lower trees, and scans are fast. This we talked about. Rules for index nodes, everything that's smaller is to the left. That's it. And then we have something called the fan out of the tree. And this, I think this is kind of the important thing. How many pointers go from a node to the next level? Because that determines the height of your tree. If there are many pointers, then that means you can fit more records in at the next level. And so that means you can, typically reduce the size of the tree. What B trees will typically guarantee you is that the storage utilization is at least 50%, meaning that it's always half full, and the average is actually close to 70%. Why is it not 100%? Because you are dynamic. You're inserting, and that means you have to do some kind of splits, and so you can't get 100%. I'm gonna actually, we did a search. Before we stop, let's do inserts and some more fun. So we want to insert 8. Now, where would 8 fit in this tree? It's smaller than 13, so it has to go here. We have trouble, right? It's full. So we have to split. And then the root is full, actually. And so when we split, we have to split the root as well. So this is what we're going to do. So we insert 8. We basically have to first split the leaf. We have to take this leaf and create an empty leaf, and we move half of it to this leaf. Then we take this middle key here and we copy this to the parent. Why this one? Because it's the smallest one here, and that means that everything to the left is smaller than it. Everything to the right is equal to or smaller. Or larger, equal to or larger. Thank you. So we maintain the correctness of the tree by picking this one. Now we could pick 4 in this case, and we'd still be correct. But it's easier to pick this one because we know it's there. Clear? Okay. So that was the splitting of the, and then we need to fix the linked list. And this is standard maintenance of linked list, right? So which you know. And that means now we have an extra node here, but we have these search key that we need to add to the parent. And now actually we can insert the 8. So this is the situation now, and now we have to split the root. And conceptually what we do is that we insert the new search key into the root. We make a new node. We move almost half of it here, and then we take this middle key and we move that to the new root. So that becomes the new root. That's the whole thing. This is called split propagation. Because everything was full, we move the split up here. You've seen something similar in tree structures? Not really. I mean, usually you sort of build it down. And remember, when you were balancing trees, you were always kind of shifting, right? You were taking one node and you were making it the root to make one part longer and the other one shorter. And this is very different. This is basically the tree grows up. First it goes out and then up. And then out some more and then up. And this is how you maintain the balance, by always splitting first at the leaves and then eventually into the nodes, and eventually, if the tree is big enough, you have to add one height to it. Yes, correct. Yes. About the pointers, are they really pointing at the first node, meaning? Okay, yes. Okay, so here. Yeah. They are. Exactly. Good point. What they really are pointing at is an address on disk, where the page is that contains the node. And so it's basically just a page address, and that page address is correctly, as you point out, so I'm drawing it in the middle is probably confusing. Yes. Yeah. Good question. Yes. Level 2. Yes. The level 2, is it not linked? In practice, you probably do have links here. They are less important than the other ones. Yeah. I think in practice they are typically linked, but because you're always almost always going to into the leaf and then scanning, then that is not really important. What would you use those for? You might potentially use them for kind of management or locking, when you are if you have to propagate locks. There's something called range locking, which we'll get into, where they might be useful, but so I think they are maintained actually in many cases. Good questions. All right. So which leaf do we insert to? Remember, after we split, where do we insert? Well, it depends on the value. 1 would go here, and 8 would go here. So this is the question here. Where do we split the leaf? Where do we insert? So when we're splitting the leaves, we just first split it. So, and that means that each leaf will have will be half full, right? Because it was completely full in the beginning, and we split it into 2 parts, so it'll be half full. And then we just put the value in the correct place. All right, storage capacity. A typical tree, let's say that the order is 200, meaning you can have up to 200 pointers. And the average utilization we said was 70%, or we can say 67%. That means that we have 133 pointers on average to the next level. So if the root has 1 page, or root is 1 node, how many nodes can be at the second level? Or if the tree is only root and then some leaves, how many leaves can we have? So we have the root here, and the root can have 200 pointers pointing to leaves. How many leaves could be on this level? Yeah, or in the order of 200. Maybe if we do as we did here, we say we have the last pointer, then 201. Yes. That wasn't a hard question. You're shy. Come on, don't be. On average, how many leaves would be in this tree? 133. I mean, that's the average fan out. How many, and if we assume again that we can have 200 records here, how many records could we store in a tree with 1 level? So with a root and 1 level. What's the maximum if everything was completely full? It would be 200 by 200, right? That's the maximum we could store in this tree. Are you with me? So the fan out is, how many pointers do you have going to the next level? Sorry. Yeah, not. It's basically the number of pointers. Yeah, on average, yes. Yeah. So if you assume utilization 67%, that's what you would get, sort of how much broader the tree is on each level. Okay. With 67% utilization, you would have something like 133 times 133, which is what? Anybody have a computer? 13 by 13, 269. 17? Can that be? For sure? 70, yeah. Yes. 176, so 18K. Okay. So a single level would be sufficient for a table with 18,000 entries. If you add 1 more level, that is, you go down here again with the same fan out, how many records could you sort of reasonably store in the index? Yeah, so you the 18K times 133, right? And so what you said, 2 million? Okay, all right. So we can do roughly 2.3 million. Do you see the growth? It's huge. And this is the exponential growth that is so nice. One more level. Where do we get? 2.3 million times 133. Yeah, so 312 million. Okay. One more level. Are we having fun yet? 41 billion. Yeah, 42 billion. Okay. So how many IOs would it get in a relation of 42 billion to find a single record? Yeah, maybe 60. You need the root, then you need this level, this level, this level, this level, this level. And then maybe you need one extra to get the actual record. So maybe 7. But that's 42 billion. If you have more than 42 billion, well, you want one IO. And that brings you to 42 times 133. That's, a trillion, right? Gazillion. So this is actually the nice things about the trees is that the capacity grows. And so as you have, for most reasonably sized tables, you only need a few levels. Now, then, because the top levels are not that big, they will typically fit in memory. I mean, the root is only 8K. The level 2 is 133 pages, it's 1 megabyte. Level 3, 133 megabytes. All this will fit comfortably in memory. So normally, for a tree that is 3 or 4 levels, you will have to pay 1 or 2 IOs to get through your relation. So that's the beauty of B+ trees, actually. You may have a lot of indexes, and so they might take up a lot of space. But again, disk is fairly cheap. But the point is how to get it. But you're asking maybe about the buffer manager. So if you have a lot of indexes, then you can't fit them all in memory. Yeah, that's a good point. Normally, there's some kind of power law to the use of indexes, so that a few of them you will use the most, and the rest you will use rarely. So in that case, you will probably, I mean, if you have something on the ID, for example, that probably gets used a lot. So yeah. So I want to point out there are some errors in the algorithm. If you want to read these, they are here. I've actually reported them to the authors, but I haven't seen them corrected. Something about deleting. Deleting doesn't happen too often, so we can sort of safely ignore this. And some practical issues. So we're out of time. We'll stop now. And then we'll see you on Tuesday when we continue. Do a little bit of this and then sorting. That's the next step. All right. Thank you. Yes. Put up the slide with the error in the algorithm. I'm sure this is the right page. I'm sure this is not the right page. It's probably from an earlier edition, actually. But the figures are there and the errors are there. So figure 911, this is the B+3 algorithm. Figure 911. I think the figure is probably, maybe the figure is even. Oh no, it's in 10 now. There's in 10. Okay. So there is. Okay. This would be the insert, I think, because it's a split. Yep. It's the insert. Insert algorithm. Tack.